minus x, you distribute these terms. So there's a z again, so we have to worry about it. We just get partial yf plus z partial yf. Also notice for any continuous functions, actually any continuously differentiable functions, you can actually commute the derivative. So partial z partial yf is the exact same as partial y partial zf. So for our purposes, we're going to assume f is one of those C1 functions. So we can distribute that, and minus y partial z squared f. Plus z, what happens when you distribute this? Well, there's no x's here, so we don't have to worry about that. We get z partial x partial yf minus y partial x partial zf. Now we're able to get down to some nice cancellation. Over here we have partial y partial zf. Now there's a zx coefficient in front of it here, and if we look for it later on, we can see there's a minus xz coefficient in front of it there. Which means the whole thing has to go to 0. Then, if you look here, there's a minus z squared coefficient. So let's add partial y partial xf. There's a minus z squared coefficient here. And if we look for it later on, wait for it, partial x partial yf, z times z is positive. So this also goes to 0. Then we have partial z squared f. The coefficient in front of it is minus yx. You wait a little bit. The other coefficient in front of it is minus x times minus y is positive xy. So this also goes to 0. Then we get a partial xf, but if you look everywhere else, it looks like there's not another partial xf, which means that this is probably standing by itself. We'll leave it be as plus y partial xf. Then we keep going. There's a partial yf, and it's also standing by itself, so we'll leave it be. Over there, you see the partial z partial yf, but we already covered our bases with that. You will also see the partial z squared f, but we already worked with that. Here you will see the partial x partial yf, but we already worked with that. The only thing left is the partial